Hello, my name is Mitsu Ganley. I'm the Director of Marketing here at Lumina Decision Systems. We're really thrilled to have Yulia and Evan here with us to talk about a project that they worked on. Yulia Chen is a PhD student at the Adam Bryant Labs at Stanford, studying greenhouse gas emissions from oil and gas operations. Her current research focuses on testing and synthesizing broader insights from airborne and methane detection and quantification technologies, both onshore and offshore applications, using a combination of engineering, field data collection, applied statistics, computer vision, and remote sensing. Yulia earned her bachelor's degree in environmental engineering and applied mathematics from Johns Hopkins University. We also have with us today Dr. Evan Sherwin. He's a data-informed energy policy analyst investigating the role of hydrocarbon fuels in a rapidly decarbonizing economy. Much of his research focuses on leveraging emerging technologies and data sets to find and fix methane emissions across the oil and gas value chain. Evan is a postdoctoral research fellow at Stanford University's Department of Energy Resources Engineering with a PhD in engineering and public policy and a master's in machine learning from Carnegie Mellon University. Evan is the founder and chair of the Methane Emission Technology Alliance International Seminar Series and a founding member on the board of directors of Climate Change AI. Evan began his career as an energy analyst here at Lumina Decision Systems quite some time ago and has been using Analytica in his research ever since. We're really thrilled to have them. So with that, I will let Yulia jump in and talk about methane emissions.
Thank you, Mitsu, for the introduction, and I'll lead the discussion today, and Evan will also host questions with me after the talk. Let me start sharing my screen. Am I sharing everything okay? Okay, cool, thanks. So my talk today is titled Quantifying Regional Methane Emissions in the New Mexico Permian Basin with a Comprehensive Aerial Survey. This is joint work by Stanford University, Kairos Aerospace, as well as University of Michigan. This work has already been published on environmental science and technology and received some news attention. So please refer to that paper if you would like to get further information. So let me first talk about why methane matters. According to IPCC back in 2010, at least methane as a really potent greenhouse gas accounted for 16% of total anthropogenic greenhouse gas emissions. And the oil and gas sector, or the natural gas and petroleum sector in the US, accounted for 31% of the total anthropogenic methane emissions back in 2017. And we think this might be a pretty conservative estimate because of many things which I'll talk about a bit later. So in the New Mexico Permian Basin, or the Permian Basin in general, methane is in headline news because there has been spiking production of oil and gas in this area in the last decade or a bit more. And conventionally, methane leaks are detected and repaired using optical gas imaging cameras and other devices on the ground. And usually what the oil and gas operators would do is to drive a truck into the field and manually survey their infrastructure with an infrared camera. And according to this survey by this study by Ravi Kumar et al., usually a crew of 2 people can sample about 6 sites per day. So more recently, remote sensing has been applied to sensing methane in the field. This is a hyperspectral sensor by Kairos Aerospace and is mounted on a small airplane, which is flown at altitude about 3,000 feet. And by using the hyperspectral camera, they are able to detect the methane, which is demonstrated here in blue and white color. The methane plume here can have concentration information, and along with the wind information extracted from other data sources, it is possible to estimate the rate of methane that's being emitted from this particular site. And Kairos Aerospace is already a very operational and mature and commercial company that has done comprehensive surveys in many parts of the US, including the New Mexico part of the Permian Basin. And this is illustrated here as the black polygon. And the way that Kairos cover this area is like this. They would first go to a subset of this area and survey a stripe of the area like this, and then they would turn up the airplane around to cover a partially overlapping area. So this way, if there are oil and gas infrastructure at the locations A and B, they could be sampled multiple times on a single day. And then Kairos would just finish surveying this entire area in a low mowing kind of fashion. So this is the coverage map of this black polygon. There are many oil and gas infrastructure here, which are illustrated here. And all of these point assets were sampled up to 16 times in the area. In total, the area that's sampled covers about 32,000 wells, and Kairos covers 90.4% of them, which is why we say this is a nearly comprehensive survey. And they also covered over 15,000 kilometers of pipelines. Everything was done on 115 flight days between October 2018 and January 2020. All of these assets were repeatedly covered on an average of 4 times. And that makes up the total number of well visits to be a number that's about 117,000. And because there can be multiple wells on a single site, we computed the average number of wells per site and deduced that the total number of cell visits is about 98,000. So that means with 115 flight days and 117,000 well visits, the speed of detection, the speed of survey is about 1,000 wells per flight day in the New Mexico Permian Basin. On the magnitude sense, that's about 100 times faster than ground-based surveys. And I will just give you the result first before I dive into the Analytica application and the methods. So our results shows that the New Mexico Permian is 5.1 to 7.5 times leakier than the GHGI estimates. With the survey, Kairos found 1985 methane plumes from 958 distinct methane sources, which is shown in this figure here. And after we have done some computations using Analytica, we found that the directly measured emissions sum up to be 153 ton per hour, with some extrapolation to things that were below the detection limits or that was not covered in the area. The total methane emissions from oil and gas operations in this area. Well, I should mention that it's only upstream and midstream, and there's nothing done to the distribution or downstream part of the natural gas supply chain. And compared to our total 194 ton per hour emissions, EPA's GHGI, greenhouse gas inventory, which is the official inventory of the US, estimates about 25 ton per hour for this New Mexico Permian area. And because the EPA GHGI was done at a time that was before a huge oil and gas production spike, so we adjust or align the EPA estimates by adding 5 ton per hour due to the production growth in this area. So you may ask why are we seeing these huge differences? And part of the reason why for that is the EPA GHGI is mostly relies mostly on ground-based surveys. And why don't the ground-based surveys see that many emissions? And here we provide some possible explanations. Number one, the ground surveys may overlook some of the emission categories, such as tanks, inlet flares, and gathering lines. And number two, which is the most important point I would like to get through in future slides, is that the ground-based surveys have very limited sample sizes, which may not capture some of the low occurrence but high consequence super-emitting events. And number three, because the survey was on the ground, operator consent is usually required for access to survey those infrastructure, and this may cause some bias in the emissions that were detected. And number four, most of the ground quantification technologies, such as OTM33A, hypo sampler, are not designed for the size of the aerially detected super-emitters, which are orders of magnitude larger than the ground-based surveys detected emissions. And lastly, we really hope that the New Mexico Permian Basin at the time of the survey was leakier than the US average due to their limited gas takeaway capacity, and because, well, the state of New Mexico was still ramping up their regulation on methane emissions during the time of the survey. And I'll go through the first two categories in detail. So firstly, the overlooked emissions. Jeff Ruseford, who is also a PhD student in our group, did the very detailed analysis of the GHGI and some other newly observed data sets of methane emissions detected on the ground. And he was able to find that tanks and other equipment leaks are very much overlooked in the GHGI. And this is also, this could explain some of the reason why the aerial survey sees many more emissions than ground surveys. Here's another example that's done by, Evan here and also Jeff. When they were doing fieldwork in Texas, it was very easy for them to detect a very large inlet flare, and this flare looks like something that's over 1 ton per hour, which is also something that were overlooked in the emission category of the GHGI. And here is now moving on to the next point of the sample size. Here's an illustration of sampling from a very heavy tail distribution. What we speculate is that the methane emissions from oil and gas sector follows a pretty heavy tail distribution. And as a pretty simplified example here, let's imagine a population of methane emissions of 101 sources for methane emissions, and 100 of them are pretty small leaks at 1 kilogram per hour, and only one of them is very large at 1 ton per hour. So the sum of total emissions of this population is 1.1 ton per hour. And here are 3 strategies of sampling this population. And strategy number 1 is to sample the entire population with pretty good sensitivity, so ground-based survey of everything. And that way we do not need to do any extrapolation, and we would know that the population emits the total emissions at 1.1 ton per hour. The strategy number 2 is to sample a small subset of about 5 leaks. And this is the logic behind many of the ground surveys. And 95% of the time, the extremely large leak would not be detected by will not be included by the sample of 5 leaks. And that's why you would think everything is 1 kilogram per hour, and the total is thus 101 kilogram per hour. And only 5% of the time, this large leak would enter the population, and you would derive something that's over 20 ton per hour. And usually in real life applications, that 5% scenario is not usually the case. And that explains why the small sample size will give you a smaller total estimate after extrapolation. And strategy number 3 is to sample the entire population with a sensitivity that's over 1 kilogram per hour. And this is very similar to the operations of remote sensing with airplanes, which cannot see every single small leaks, but it's able to detect the large ones. So with this strategy, the technology can only see this one single large emitter. And you will know that there should be something that you need to do to understand what's the additional emissions from the small leaks. However, at least you will know that there are at least 1.1 ton per hour from this population. And the takeaway message from this exercise is that it's probably better to be roughly correct than precisely wrong. And that's why it's important to draw implications from strategy number 3. Okay, and here's another illustration of what we found in the field. Kairos was able to do 98,000 site visits in the New Mexico Permian Basin, and they found about 2,000 plumes. So what if we draw from this population and treat it as truth, and then usually this will follow a pretty less steep, the cumulative probability curve. Oh, I should mention that the x-axis here is the fraction of measured total well-site emissions after scaling up, and the mean measured total emissions, which is the black dashed line in the middle, demonstrates what Kairos found was the 98,000 site visits in the field. And if we sample 98,000 times, then the cumulative function would look like this. However, if we only do 100 sample sites, then there's a 34% chance of none of the Kairos detected plumes would enter the sample, and thus the total would be a 0. And there's also a 72% chance that the 100 sampled visits after scaling up would give us an underestimate of the total. Even increasing the sample size to 1,000 or 10,000 wouldn't solve much of the problems, because the cumulative function would still look not steep enough. That's around 1 here. And this sampling exercise tells us that in cases of the sampling from a heavy tail distribution, like the methane emissions from oil and gas sector, a population survey is key for getting us the right amount of total emissions in the area. And by adding up everything as the fraction of total measured emissions in this area, and as well as the size of these methane emissions, we found that about 50% of the emissions are from the very, very large emissions, emission sources that are over over 300 kilogram per hour. And some of the top 10 leaks, some of the top 10 emission sources are just account for 1% of total emission sources. They're responsible for about 10% of total emissions here. And so how does this look compared to the ground-based surveys? O'Mara et al. Did a synthesis of about 11 studies in the US, and the site level emissions, and compiled a sample of about 1,000 site level emissions. And the largest one from the 11 studies that compiled by O'Mara et al. Found that it is 0.287. That means it's only able to find less than 47% of total emissions. That means the ground-based surveys, which also sample small subsets of everything, can have some biases, because 53% of total aerially detected emissions are from persistent average sources larger than the largest ground detected source. So there I've talked about why the ground surveys cannot see the very large leaks, and explains part of the reason why there's a large divergence between the ground-based estimates and the aerial-based estimates. And why are we confident in our large emissions estimates? And there are three things that we have done. Number one, we did single-blind testing of the instrument and very strong uncertainty quantification with Monte Carlo simulation in Analytica, as well as sensitivity tests to understand the lower bounds of the total of the total emissions. So here's some pictures for number one, the single-blinded testing of the instrument. In October 2018, we collected 234 data points in Sacramento, in somewhere that's close to Stockton, California. And so we controlled release some of the methane from these compressed methane tanks. And so the size of these methane control releases size from 18 to 1025 kilogram per hour. This is the size of the control release is about 10 times bigger than other studies. And we do this because this control study is tailored for aerial technology that is only able to see pretty medium to large emission sizes. And the results looks pretty great. By using the high resolution rapid refresh wind source, Kairos was able to get a slope of 0.88 and the R-square of 0.67, and there's not much of a bias issue with the release rate and the reported release rate. And the detection probability is about 10 kilogram per meter per second of wind. The detection probability has this unit because the stronger the wind blows, the less the smaller the concentration will be at a certain specific methane release rate. And what this means here is that at 3 per second of wind, Kairos would see 30 kilogram per hour of methane emissions about half of the time. And the full detection limit reaches about 14 kilogram per meter per second wind. And usually they would see nothing if the emissions is below 4 kilogram hour per meter per second wind. And moving on to the second point, which is uncertainty quantification with Monte Carlo simulation in Analytica. Here is a graphic of what we have done of all of the steps that we do to get our directly measured total emissions in the New Mexico Permian area, as well as the total emissions after extrapolation. And let me go through this graph step by step. So firstly, we calibrate the 1958 methane plumes from the data set. And we do this by getting our data from the control releases. And the fitting one that we use is the log transform fit. Or, well, more precisely, it's a power law fit. And after the calibration, we select one plume for each source. As I mentioned, there are about 2,000 plumes for just 1,000 source. And that is because these sources were inspected multiple times, and sometimes but at each instant they can only be emitting at one certain emission, at one certain rate. So this is a step that we carry out in the Monte Carlo simulation by selecting only one plume for each of the emission source. And the next step will be accounting for intermittency, and what we mean by that is illustrated here. Let's imagine that infrastructure was sampled 3 times, and only at the first time it's emitting at 1 kilogram per hour, and the second or the third time it's not emitting at all. So sorry, this is a bit wrong. In this case here, the probability of leak should be 1 over. So it should be 1/3, not 2/3, because it's only observed with emissions 1 out of the 3 times. And well, observing one asset multiple times can have implications on the intermittency of these emissions of almost all the assets in this area. So, for example, we have 3 similar assets, and 2 were found. Oh, sorry. Yeah. Sorry, the graph was right. The probability of leak is 2 out of 3 because there are two leaks out of 3 times. And yeah, so what if we are sampling 3 different assets at the same time, and you found 2 out of the 3 assets to be emitting at the time of the observation, then the probability of leak would also be 2 out of 3. So the large sample size can automatically account for the intermittency. But on a single emission source level, our persistence value is computed as the number of plumes that was detected from this emission source over the total number of observations of this source. So after getting the intermittency accounted for, we can compute the directly measured emissions from this source. And here is an illustration of the 153 directly measured emissions, and this is broken down into the category of the emission source, including well sites, gas processing plants, compressor stations, tanks, and pipelines, and some other or ambiguous source that we cannot categorize. And this graph here has the x-axis on a log scale. So as you can see, almost all of the categories exhibit heavy-tailed distribution, with some of the emission sources to be very large compared to most of the smaller sources. And okay, so after we get the directly measured emissions, it's also important to account for the partial detection range. So in this example here, if, for example, Kairos detected 8 out of the 33 emissions that's between 6 and 8 kilogram per hour per meter per second of wind, then we can imagine that there are 25 methane sources or emission incidences that were missed. So this is how we account for the partial detection emission, just by filling these bars by understanding how much was detected and how much was missed. And the next step is to account for things that are below the detection limit. And this is something that we cannot understand entirely simply with the Kairos data, because the Kairos data does not include things which are below its minimum detection limit. And the way that we do this is to go back to the ground-based literature. And we simulate the wind-independent methane emission rate by dividing the 1,000 O'Mara et al. Site emissions with New Mexico Permian wind. And by doing that, we see that about 7% of total emissions on average will be missed by Kairos because it's below the Kairos minimum detection limit. And Kairos can only see 63% of if the entire population follow the distribution of the O'Mara et al. Site synthesis data set. And by Albers et al.'s accounting, the U.S. supply chain, the U.S. upstream and midstream supply chain, leaks at a rate of 2.2% of total gas production. And that means about 0.8% of the total emissions from this data set cannot be detected by Kairos, or will be under the minimum detection of Kairos Aerospace. And if we multiply the 0.8% with the gas production rate in this area, this is how we account for the total emissions that's below the detection limit. And the last step is to extrapolate to all assets in the survey area. Kairos did not survey every single wells. They surveyed 90.4% of wells. And we do this extrapolation by simply dividing the emissions from the last step was 90.4, assuming that the wells that were not covered have similar emission profiles as the wells that were covered. So after these extrapolation steps, we can get the total emissions, which is about 194 on average. And the Monte Carlo simulation in Analytica enables us to do the uncertainty quantification, which are shown as a 95, sorry, this is the 95% confidence interval of the total emissions. And lastly, Analytica also helps us do sensitivity tests. The base case, as I mentioned, has 194 with some total emission rates that's, with the 95% confidence interval about 70%, as about 70 tons per hour. And what if we disable extrapolation to assets that were not covered? This is by assuming that things that were not covered does not emit at all. I know this is not a reasonable assumption, but this gets at the lower bound of total emissions in the area, and that will still get us a 167 tons per hour. Or what if we exclude everything that's below the minimum detection, which is, well, if we do not add up the 0.8% multiplied by the gas production, the total emission will still be 177. And what if we exclude the top 20 plumes? That is by assuming that about the 1% of plumes are all outliers and should not be, and are usually not the case in any normal or reasonable data set. Then the total emissions estimated will still be higher up in 173 tons per hour. And lastly, what if many of the uncertainties are from the HRRR wind or the high rapid refresh, which is a data set that's provided by NOAA, and replace the wind data source as dark sky, which is a proprietary wind estimation or a product. Then the total emissions retrieved on different days will be a little bit different, but still pretty high. And the fractional loss rate is computed as the total methane emissions divided by the total methane production in this area. And the base case says that 9.4% of the gas that's produced will be leaked into the atmosphere throughout the midstream and the upstream supply chain. And no matter how we compute it, the lower bound mean estimate is still at least 8.1%. And so in conclusion, the aerial surveys unveils many super-emitters which were never detected in previous ground surveys. And we think this is an important thing to note because methane emissions matters, and the current estimate or the current inventory is likely an underestimate for total methane emissions from the oil and gas operations. And one key, especially in the New Mexico Permian Basin at the time of the survey, the methane emissions appears to be very high. And one key reason for this underestimation in the inventory is because a population level comprehensive survey is key for sampling from a heavy tail distribution. And lastly, we drew confidence in our estimates from blinded testing of the instrument, sensitivity test, and Monte Carlo simulation with Analytica. I would like to acknowledge the funding by Natural Gas Institute of Stanford University for making this project possible. And thanks, and here are some of our co-authors, as well as Kairos Aerospace and the analysts from Kairos Aerospace for providing us data for doing this analysis, and other students in our group for making the control release possible to verify the instrument. Okay, thank you.
Thank you so much, Julia. It's very interesting. We love that you used Analytica for this project too, of course. So now if anybody has any questions, we'd love for you guys to chime in. You can drop the questions in the Q&A or the chat feature. or you can raise your hand and we can actually give you the ability to speak. While we wait for questions to trickle in, if there are any, I do actually have one for you, you and Evan. My question is there anything being done with this study, with these findings, and kind of what are the next steps, or has this evolved into anything?
Okay, great. So yeah, these, well, as Julia pointed out at the beginning, this paper has made a significant impact. It's gotten a fair amount of media coverage, and
yes, which is great.
yeah, it's really helped shape the narrative around methane emissions, both among regulators, in industry, and in the and among environmental nonprofit organizations. So we've presented these results multiple times and sort of in different stages of its development to the Environmental Protection Agency. Julia was featured in a workshop they held recently this past year. We have been in discussion with a number. We work closely with industry partners, not just methane sensing companies, but also with operators who are working to, oil and gas producers who are working to figure out, well, how do we reduce our emissions? And this, yeah, it's a hopeful story.
Yeah, no, I feel like the information is so valuable. And I know that you guys have gotten a ton of coverage on the topic in your findings, which is fantastic. Congratulations to you both. I was just curious, how does this information get from here to the people that are making the decisions, or, putting regulations around some of these industries to make sure that it's being utilized? So, fantastic. That's great to hear. All right. We'll give people a few more seconds if they want to put some questions. Oh, great. We had one come through. So Lonnie Chrisman is our CTO, and he just chimed in with a question. Have you computing the value of your analysis and scanning tech?
Sorry, what is scanning tech?
Oh, I think Lonnie just means the aerial methane sensing technology.
Okay. Yeah, Evan, would you like to take this one too?
Sure. So it's the short answer is we haven't directly done this sort of value of information analysis. I think it would be a really useful exercise. It's a difficult question to answer based on our current level of understanding. This type of approach gives us, as Julia pointed out, a very good estimate of total methane emissions if we were to take a snapshot of every single asset that there is in a given region. But in order to compute the value of information, and presumably most of this value would be in reduced emissions and even in improved, increased sales of natural gas that is no longer leaking, then we'd need to be able to say, well, the airplane flew over a well site and found that there was an emission. This emission was fixed. Well, how long would that emission have been there in the absence of the airplane? In the absence of this repair. That's this question of emission persistence is something that's really an active area of research that we don't have a clear answer to yet. I think the short answer to your question is that the value of, and it's also kind of a philosophical question. What's the value of this information? One is, what's the value of the reduced emissions as a result of flying the campaign? But then, well, what's the value of the regulators and industry understanding the magnitude of the problem in the first place and taking action to reduce these emissions on a much broader and more proactive scale? I think that the answer to both questions is very high, and they're actually, Kairos Aerospace has conducted an analysis with an operator called Triple Crown that they partnered with, where Triple Crown actually made money on the whole operation, irrespective of greenhouse gas emissions, just based on being able to sell the gas that they didn't realize that they were leaking. They made money on the whole thing. So the return on on this type of survey can be very high.
Great. Okay. Evan, I know you worked with Lumina some time ago, but do you want to speak about some of the projects you've been on or your background here?
Sure. So I started working at Lumina in 2011. It was my first job out of undergrad. I feel so lucky that I found this cool job listing, and that was able to work for 3 years with Max Henry and Lonnie Crispin and so many others on on the Lumina team. And I worked on quite a few different things, but the sort of flagship projects, one was a website called megajoule.org, aiming to provide a platform for energy related estimates and projections, like how much a battery is going to cost in 10 years. There's so many different estimates out there, and we wanted to provide sort of a single place where people could put those. And that's still, I think it's still up in some form. But I then transitioned to more of the modeling side of things, and worked on electric power system simulation tool for the California Energy Commission. Probably the bulk of my work, my sort of the thing that I contributed to most was a model of the U.S. transportation system, vehicle transportation, focusing on light duty and heavy duty, called the Analytica Transport Energy Assessment Model, 18. The part that I really focused on was the biofuels module, looking at what exactly there were all these questions around the renewable fuel standard at that time, and we were starting to hit the limit of how much ethanol could even be blended into the gasoline supply, and all of a sudden there was this volumetric limit on or requirement of blending, and gasoline demand actually went down, I believe, a little bit. So it wasn't clear whether it was even possible. So I was looking at some different opportunities for for how to comply with the renewable fuel standard, and what might be some of the most effective approaches for promoting some of these alternative fuels. So I dug in a lot to the it was a time-based simulation, so a lot of work with the dynamic function within Analytica. And all this really served as a basis for I realized a couple of years in, well, I really like this type of work, but if I want to keep going in this direction, I should probably get a PhD. And the work that I did at Lumina really provided a foundation for my dissertation work. Every single project that I've worked on just about has had a significant Analytica component. In the optimization-based techno-economic assessment of renewable jet fuel, which I presented on at the Lumina webinar a while back, that's all coded up in Analytica. And it's not just because I worked at Lumina that and I'm familiar with Analytica, that I've been using it ever since. I know how to program in Python, R, and several other languages. And it's not just because I'm giving speaking at an Analytica webinar that I'm saying this today. I really do find it an extremely valuable tool, and really maybe it's just for the way that my brain works. I can write models so much faster, more effectively, keep track of what I'm doing, and make big changes to the model pretty late in the game, which is much harder to do when you've just got a big thing of code. So there's, it's a tool that I really value, and it's been wonderful to continue to work with Lumina. Max and I worked together on a project just about a year ago. So I'll end there.
Well, thank you so much. it's been a pleasure working with Yulia and Evan and putting this event together. A couple of quick notes for those who are attending. We'll send out an email after the fact. We'll link the study, the published paper that Yulia and Evan have. I'll put the jet fuel webinar link in there as well if people want to check that out. And we also have an upcoming webinar on Tuesday, October 11th at 10 a.m. Pacific Standard Time. And that's going to be on navigating the heat pump landscape, helping consumers, utilities, and cities make economic decisions. We're really excited. We'll have our very own James Milford, the director of our consulting services here at Lumina, leading a panel of experts, including Justin Spencer, who's the project director at Apex Analytics and heavily involved in heat pump conversations online from what I've seen, as well as Brian Thole, who's an energy services supervisor with the city of Fort Collins, Colorado. So that should be a really interesting talk as well. And again, thank you for joining us. Thank you so much, Evan and Yulia, for putting this together. And we'll let you go. Bye.
Thank you, Mitsu.